Okay, so hello everyone. Can I just make sure that you can hear me? Does everyone hear me? Is this working? Perfect. Thank you very much. Um, Thanks for this. This is great. Okay, so hi, my name is Nicholas. Yeah, I don't know any of you. You don't really know me because you're doing a different course, but I think the material is very similar. So I'm going to do a review session for your exam. Um, the idea of today is that I'm just going through a past exam, and then I think you also have access to. It's an exam from 2020. I have slides for the whole exam. We're going to go as far as we can in the exam, most likely in the 90 minutes that we have together. We won't get through everything, but that's okay. And I mean, I don't have access to your course or anything, but I will share the slides that I've made for which contain the solutions to the full exam with the administrators who set this up so that they can send you these slides so that you have access to them. And also this meeting is being recorded, so you can rewatch everything and see the explanations if you want later on. In general, while I go through things, please just ask questions. I think hopefully you can unmute yourself. Otherwise, just like raise your hand or write in the chat. I think this should hopefully work without an issue. Um, okay. So can you see you can hopefully you can see this you can hopefully see this. I can't, yeah. I can't really see you anymore because I'm now looking at my own slides. So really the ideal thing is that you just speak up or you just maybe if you raise your hand, there is a thing that pops up. Um, but if you just write something in the chat, I don't know that I see it. Okay. And I think the ideal thing is that you just ask throughout, but of course in the end we'll have a few minutes as well if you have some more questions. Okay. Perfect that you see the slides. That's great. Okay, so the administrative part is less for you. That's more for the students that do the online course. This exam sort of has two parts. So the slides will be sent to you afterwards. I don't have access to your course, so I will email the slides afterwards to the administrator who sent this up, and they will send them to you. This is a past exam from 2020. The material is the same, so you should be able to solve all of this. And you will get all of these slides, this whole deck of slides at the end, and then you will have access to everything, but you don't have access to it now while I'm going through it. Um, okay, let's start. So this exam sort of had two parts. Part A consisted of 5 shorter questions where everything had to be solved. Part B consisted of multiple questions where you had to choose multiple questions that were longer and where one had to choose which questions to answer. This is not necessary. I don't know how your exam is. I have no idea about, so do not talk to me about this particular structure question. But we are just going to start from the beginning and we're going to get as far as we get. Most likely, I mean, I'm sure we're not going to finish, but these slides contain the solutions to all questions in this exam, right? So you have a lot of practice material in these slides. Okay, so let's start. The first question starts with the regression model where y is regressed on x and u. U is the error term, x is the regressor of interest. Yeah, so the error term has 0 mean. It has a variance that's equal to sigma squared divided by x squared. And it has no serial or no autocorrelation or no covariances between the u's and between ui and uj, or no covariances between two u. Yeah. You are given a sample of observations, meaning you have y and x in your data set, which you have n observations of each y and x. You're also told that you can treat x as being non-stochastic. For now, let's ignore this. We'll get to this in a few slides. And then there are two questions. Let's first look at question A. Question A says, derive the OLS estimator of beta. In the presence of heteroscedasticity, the OLS estimator is unbiased. You're not asked to show this. Derive the variance of the OLS estimator beta. So there's sort of three parts to this. Let's just start with the first one, which is deriving the OLS estimator. Okay. So hopefully by now it's quite clear how we derive an OLS estimator. We minimize the sum of squared residuals, while u is equal to y minus beta x. So it's equal to minimizing or to finding the beta that minimizes the sum of y minus beta x squared, right? And so you want to solve this problem. How do you do it is, well, you take a derivative, you find the first order condition, right? And so what's the derivative of this whole thing here with respect to beta? Well, first you do the outer derivative, so you get 2 times the summation of y minus beta x. And then the inner derivative is minus x. So you have minus 2 summation x times y minus beta x is equal to 0. Right? So that's the first order condition. What I also do is once I start being in the first order condition, I add the hat. Right? Why is this? Here, beta is the true population parameter. This is the number we don't know. And we will never know it. And what we're doing in OLS or in any of these estimation methods that you've been learning is we are estimating it, right? And the estimate is the thing that's going to get a hat. And here you're getting at the estimator. So at some point in this derivation, you have to add the hat. You cannot add it here. Here it's wrong, but anywhere as of here, it's correct to add it. Yeah, at the latest here, you have to have a hat. I always do it as of the first step. Okay. So now from here, what can we do? Well, we can divide both sides by minus 2. So you're left with this. Then you can multiply this out. So on the left-hand side, you're left with summation of xy. And on the right-hand side, you're left with the beta hat times the summation of x squared. And then you can divide by this and you have the OLS estimator. Yeah. Which you probably know that this is the right solution, which is quite nice in a question like this because you can sort of check yourself if you have the right answer. Yeah. The important point is to realize that this question says derive the OLS estimator. And so if you just write down the solution, you will get kind of points deducted. Yeah. In general, if it says derive, you have to derive the answer. The second part was just this sentence, which is saying in the presence of heteroscedasticity. So this is sort of a thing that you should notice just when you read the question. It tells you that the variance of the error term is equal to sigma squared over x squared. Right? So if the variance of the error term is constant, just sigma squared, then we call this homoscedasticity. But here, this depends on x, right? So it varies with different values of x. You know? And therefore, you're in the case where you have heteroscedasticity. But this is just a statement that tells you, okay, the estimator is still unbiased, but we're not asked to show this, so we can just go to the next part. Derive the variance of the OLS estimator. So to derive the variance of this OLS estimator that you just found, what do we do? Well, the first step is always the same. The first step is always the same. The first step is to plug in the model for y into this formula, right? So we have beta hat is equal to the summation of xy, but y is equal to beta x plus u divided by the summation of x squared. If you multiply this out, you get that beta hat is equal to beta plus summation of xu divided by the summation of x squared. Okay, and so now we are at a point where the variance of beta hat is equal to the variance of beta plus this fraction. Yeah. Now comes the part that is important from the question. In your lectures, oftentimes when you found the variance of an estimator, what you did is that you looked at the conditional variance, right? So you looked at the variance of beta hat conditioning on x. And why did we do this? Well, we did this because once you conditioned on x, you were able to treat x as a non-random variable, right? It became sort of like constant. Yeah. Why do we not have a conditioning on x here? Well, the question says you may treat x as being non-stochastic. This means nothing else as you can treat x as being constant. Yeah, it's a not, we are treating all these things as random variables. Here, x is not a random variable. So you can just treat it as being a constant. And so we don't really have to condition on x here because it is already constant. Yeah, that's all this is doing. Okay, so the variance of beta hat is equal to the variance of this fraction, which is here. And now we apply sort of the variance formula. And so what do you get? The first term is the variance of beta, but beta is a constant, right? And so the variance of a constant is 0. Great. The second term is the variance of this part. X's are constant, but u is not. So this term will stay. So you have the variance of this fraction. The third term is the covariance between beta and this fraction. But the covariance between a constant and something that's not constant is 0, right? So you're only left with this thing here. From this to this step, this is completely voluntary. You don't have to do it, but it's just a notational thing. Because these x's are non-stochastic, I'm just defining a variable d that is equal to x divided by the summation of x squared. And so it's just a notational thing. You do not have to do this. The result is exactly the same. The steps are exactly the same if you don't do this simplification. Yeah? Okay. So now we are here, and we want to figure out how do I simplify this. Here I've written down that this variance of the summation of d and u is equal to whatever this is plus whatever this is. So instead of trying to convince you what this is, let me just show you why that's the case. Let's consider a very simple case. Yeah. Suppose instead of having the variance of the summation of di ui, where I goes from 1 to n is just equal to 3. So we just have 3 observations. Let's make this very simple. Yeah. So then what is this equal to? Well, this is then what? This is then what this is equal to, right? You just n is equal to 3. So this is then just what? Is the variance of d1u1 plus d2u2 plus d3u3, right? It's just the sum of diui from 1 to 3. Here are these 3 sums. Okay, next step, let's write this variance out. Let's apply the variance again. So what's first step going to be? You get the variance of d1u1, variance of d1u1. Second, variance of variance of d2u2, variance d2u2, plus variance of d3u3, plus variance of d3u3. Now you need to do each of the covariances, right? So the covariance of d1, of the 1 and the 2's. So covariance d1, d2, u1, u2. Covariance of 1 and 3. Covariance d1, d3, u1, u3. Covariance of 2 and 3. Covariance d2, d3, u2, u3. Yeah? Next, what do we remember? The d, right? The d is only a function of x. And x is non-random, right? It's non-stochastic. What does this tell me? Well, this means that out of all of these things, for example, out of the variance of d1, u1, I can take out the d, right? I can take out the x. So then I have what? Variance of d1, u1 becomes d1 squared variance u1. Similar for variance of d2, u2, d2 squared variance u2. Variance of d3, u3 becomes d3 squared variance of u3. Similarly for covariances, d1, d2 can be taken out, and you have d1, d2 covariance u1, u2. Okay, you get the point. Similarly for the rest. And then you can bundle this together. Here in the blue now, I have the first 3 terms are just variances. So it's the summation of I1 to 3 of the variances of ui, and in front of the variances, you just have always di squared. And the second part are these covariances, where again, you sum over these covariances, right, of always I and j, where I and j are just not the same. Yeah. And this similar idea holds for any n. And that's exactly this formula here. Okay. So now we know that we have the variance of beta hat, which is equal to the variance of the summation of d times u, which is equal to the summation of d squared times the variance of u plus the summation of di dj times the covariance of ui uj. The next thing to note is that this covariance here, I'm going to tell you, is equal to 0. Why is that the case? Well, the covariance of ui and uj is by definition equal to what? It's equal to the expectation of ui and uj minus the expectation of ui times the expectation of uj, right? But what are we told about our errors? We're told that the error term has mean 0 and that the expectation of ui uj is equal to 0. Sorry. Right? So this covariance here, these two means are 0 because the error is mean 0, and these covariances are also 0. Yeah. So this means that the variance of beta hat boils down to just being equal to this, the summation of d squared times the variance of u. And we know what the variance of u is, because the variance of u is given in the question as being sigma squared divided by x. So the variance of beta hat is equal to the summation of d squared times the variance of u, which is sigma squared divided by x squared. From here to here, I'm just plugging in d again. What's d? Well, d is x divided by summation of x squared, but then it's d squared, so you have to square the whole thing. You simplify, and you get the variance of beta. The variance of beta hat, sorry. Okay? So I did a lot of steps here, but this is sort of to show you that, I hope you've done a lot of derivations of variances by now, but you need to show every step that you're doing, and you need to explain why something is equal to 0 or why a term falls out or why something is so. Huh? So the only thing that I did in the derivation, which maybe you wouldn't have to do in an exam, is explaining this, right? If this is like blatantly clear to you, even better. Yeah, but I just tried to do this because sometimes people get a bit confused. Okay, so we're done with question 1a. Part B is discuss how you can obtain the best linear unbiased estimator, which is the blue estimator of beta, given the heteroscedasticity. So here I think it's a little bit, a good start would be to explain why this question is like kind of makes sense or is phrased this way. The point is to realize that the estimates are not blue because of the heteroscedasticity, right? So there is something that you've been talking about a lot, which is the Gauss-Markov theorem or the Gauss-Markov assumptions, which is basically when these assumptions are satisfied, right, then OLS will deliver a blue estimate, a best linear unbiased estimate of beta. And best in this world means what? It means sort of most efficient. You can think of this as just smallest variance, yeah? Most precise estimate, yeah? I would strongly encourage you to write down the Gauss-Markov conditions, all of them. Whether you do this whenever it comes up in a question, or whether at the beginning of the exam you just make like, look, here are the Gauss-Markov conditions, all these assumptions, and I'm going to refer to the relevant ones from whatever question I'm in. That's sort of up to you. But I think it's good to show that you're aware of them and that you know when and how they're being used, right? And so the point is, if you write down those Gauss-Markov conditions or assumptions, or if you go look at them, what you will see is that one of those conditions is homoscedasticity, yeah? But in this model, we don't have homoscedasticity. We have heteroscedasticity because this variance here, the variance of u, is sigma squared divided by x. It depends of x. It varies with x, right? So we have heteroscedasticity. And so the OLS above that we've just done in part A, that estimator is not blue, right? It's not the best estimator in the sense that it's not the one that attains the lowest variance. Yeah. And so what we want to do, or what this question is asking you, is how can you obtain a blue estimate? And so what you have to do is you have to somehow think, how can I transform this model so that it is blue, meaning so that it satisfies the Gauss-Markov conditions. The only thing that this model doesn't satisfy in the Gauss-Markov conditions is the homoscedasticity assumption. So you really have to just think about homoscedasticity. Yeah? Okay. So the way I do this is I think of this line, but I think of it from the back. So let's start here. Why do I start here? Well, the aim, I need to satisfy the Gauss-Markov conditions, so I need to have a constant error, right? So the variance that I want to get is going to be the variance of sigma squared. Yeah? Sorry, the variance of the new error is going to have to be equal to sigma squared, something that's constant. Yeah? Now, what am I doing here? Well, here I'm saying, first, let me just write down this fraction. What's this fraction? This fraction is the variance of my current model. This. Yeah? That's sigma squared divided by x. Now I know this is the variance that I currently have, and this is the variance I would like to get to. So now I'm asking myself, what do I have to multiply this fraction with in order to get sigma squared? Well, that's x squared, right? Great. So now I'm here. From here to here, it's relatively simple. I'm just keeping x squared, and I'm just rewriting variance of u instead of this fraction. And then from here to here, what I'm doing is, well, again, I'm saying I know that the x's are non-random, so I can just put them into the variance, right? This is the same. And this is the solution. So while the variance of u is heteroscedastic, meaning that the variance varies with x, if you were to look at the variance of x times u, you get something that's homoscedastic. Yeah, this is what this is telling you. And so what this is telling you is that if I just multiply my model by x, I get an error term that's homoscedastic. Yeah. So this is the new model, right? Before the model was y is equal to beta x plus u. Now we just multiply everything, both sides by x. So you have yx is equal to beta x squared plus ux. You could check, the error is still mean zero, right? The expectation of ux is equal to zero because x is non-varying. You can take it out, still the same. The variance of u times x, well, we just looked at this, that's sigma squared. And there's still no autocorrelation between those two errors, between ui xi and uj xj in the model, right? And so you could, if you wanted to, though this is not part of the question, write down the new estimator, but this new estimator will now be blue, because it satisfies all the Gauss-Markov conditions. This last sentence you also don't have to do, but this transformation procedure is called, in theory, weighted least squares. Yeah? Okay. Am I missing any questions so far? I hope not. No. Okay. Second question. We're going to consider the simple linear regression model where we regress y on a constant, on an x, and on an error. But in the first line already, something should stick out. We have correlation between x and u. Yeah. So again, think of your Gauss-Markov conditions. What is one of them? One of them is exogeneity. Yeah. It's violated. Right? If you have correlation between x and u, it means we are in a case where we have endogeneity. Yeah, so we will need some sort of an instrument to take care of that. Okay, the regressor exhibits sampling variability under the assumptions of homoscedasticity and an absence of autocorrelation. The IV estimator of beta that uses the instrument Z has the following asymptotic variance. We don't need to prove this. You can just take it as a given. It's given by whatever this is, yeah? Where this R squared here is the sample correlation between X and Z. And this sigma squared U is the variance of U. Okay. Give the formula for beta hat IV. So notice when it says give the formula, you don't have to derive it. Yeah? Okay, so then you can write one of two things. I would strongly urge you to write the first one. The estimator is what? It's equal to the summation of Zi minus Z bar times Yi minus Y bar divided by the summation of Zi minus Z bar divided by So someone is asking if I write the full assumptions at the beginning, do I have to make reference to the first page every time? No, I think if you just write MLR 1 to 5, but just make sure you reference the first one. The right assumption that how you numbered them. But also, writing page 1 or not is not gonna be that much time consuming. Okay, so this is the IV coefficients, IV estimates that you have, right? This is the same as saying it's the sample covariance between Z and Y divided by the sample covariance between Z and X. You can write either one or both. You don't have to write both. The important thing is if you do write the one on the end here, you have to write sample, right? Because if you were to just write covariance, it would hint at the fact that you're thinking of the population covariance, and we don't know that. The point is it's the sample covariance. You're using the sample to estimate the covariance, right? And people tend to forget the sample part, hence why I would advise you to do this. Okay. Provide at least 3 factors that will help obtain more precise IV parameter estimates for beta. In your answer, explain why the precision of parameter estimates is important. So recall the variance formula that was given in this question. Notice one thing that we can rewrite this as follows. We keep everything the same, except that here in front of the summation, we're going to multiply by 1, which is n over n. Yeah. But then I can also multiply by n over n, which is equal to n times 1 over n. But 1 over n summation of x minus x bar is the sample variability of x, right? And so now this variance basically has 4 components, the sigma squared, the n, the sample variability, and 1 over r squared. Yeah. And the question is asking you, what will help us get more precise parameter estimates for the IV estimates? Well, more precision means lower variance, right? So basically now you have to answer, well, which of these things have to move up or down in order to reduce the variance? Yeah. So we could increase the sample size, we can increase the sample variability, we could reduce the variance of the error term, and we could increase the correlation between X and Z. Yeah. So I'm giving you here 4 factors. You only have to state 3, of course. Why is the precision important? Well, here you want to talk about hypothesis testing probably, right? Ultimately, what we're doing is we have some hypotheses that we want to test, and we want to find out whether we can reject or whether we fail to reject the null hypotheses, right? As a quick aside, you never ever say or write that you accept a hypothesis, please, because that is wrong. We reject or we fail to reject. And the more precise your estimates are, the more confidence you have about your solutions, right? That's basically a good answer to this. Question 2C gives you a statement that you should discuss. The statement is, if X is not correlated with U, the best choice of instrument is using the regressor itself. So I think there's 2 ways of thinking about it. The first thing to do here is just to focus on this part, right? If X is not correlated with U, well, notice, go back here. X being correlated with U was the thing that made X being endogenous. It was the thing that violated the Gauss-Markov assumption. Yeah? Okay, that's the first thing. So if X is not correlated with U, this now means X is exogenous. Yeah? Great. So now instruments need to have two conditions, right? One is exogeneity, which means that the instrument Z has to be uncorrelated with U. But now we are being told X is uncorrelated with U, right? So that condition is sort of satisfied. It's exogenous. The second thing that the instrument has to have is that it has to be relevant, right? We want a strong first stage. And the first stage means what? It means that the instrument has to be correlated with the regressor of interest, in this case, X. Yeah. And so what's the variable that's the strongest correlated with X? Well, it's X itself. The issue is, of course, that usually when you do IV, X is not exogenous, but now we're saying X is exogenous, right? And so then X is indeed the best um, the best the best instrument to use. Yeah. And so you can see what happens to the variance, for example, because if you look at the variance, this R squared here is going to be equal to 1, right? Because it's the correlation between X and Z. But if you're using X as the instrument, it's the correlation between X and X, which is equal to 1. And so the variance basically collapses to the what should look like the OLS variance. If you look at the formula, if you plug in X in the place where you would have a Z here, this looks like the OLS estimate, right? And so indeed, it also does make sense. This just becomes OLS, yeah? And indeed, OLS also happens to be blue here because as you can see, you have a linear model, sampling variability is given, you have homoscedasticity, you have exogeneity, so then OLS is just blue, yeah? Okay, so I hope this makes sense. Okay, question 3 switches to time series. Excuse me. It says consider linear regression model. YT is regressed on alpha plus beta xt plus epsilon t, where the zero mean error epsilon t exhibits some autocorrelation, but of an unknown form. Uh, sorry, where the error exhibits some autocorrelation, this epsilon, and we are assuming that our processes are covariant stationary and exhibit weak dependence. The error and regressor may be assumed to be independent. Okay, so here there's some definition. The first question says, explain what it means to say that this process epsilon t is covariant stationary. Provide an intuitive discussion of the requirements and indicate why these requirements are desirable. Yeah. Okay. So first thing you do is you just state the definition. State the definition. Yeah. So this looks something like this. We say that this process is covariant stationary if the following holds. First condition, the expected value of epsilon t does not change over time and is finite. What this means in math is that the expectation of epsilon t is equal to mu for all t. So the crux to notice here is that this mu does not depend on a subscript t, right? It's just a constant. The variance of epsilon t exists and also does not change over time. Yeah. Again, the variance of epsilon t is equal to sigma squared. The point here is sigma squared is just some constant. It does not have a subscript t, so it does not change over time. And then the covariance of epsilon t and epsilon t plus h. So h is just some distance of time, right? So epsilon t could be today and epsilon t plus h could be tomorrow. So t plus 1, right? So h would be 1. Yeah. But it could also be epsilon So today and tomorrow, or tomorrow and the day after, right? The point is that this covariance only depends on the distance of time, which means the covariance of epsilon t and epsilon t plus h is equal to the covariance of epsilon s and s plus h. Yeah. So just to make it clear, this if h is equal to 1 day, this says that the covariance of epsilon today and epsilon tomorrow is the same as, for example, the covariance of in 3 days from now and the covariance in 5 days from now. Yeah. Okay. So it's the distance is always 1 day. Today, tomorrow, 3 days, 4 days, and 5 days. Right. So the distance is 1 day, 4 to 5, or today to tomorrow, but the covariance is the same for those two. Yeah. Okay, so the covariance depends on the distance. So in short, or in kind of words, if you want to say this, what these conditions say is that the mean, the variance, and the covariance are independent of time. You know, a slightly more technical way of saying this is that the first and the second moment of these distributions are independent of time. Yeah, the first moment, because the expectation is the first moment, the variance and the covariance are the second moment. Someone asked the question. Yes, and the covariance, not the variant, not just the variance. But you can say that, yeah, but I mean, I don't know. So I don't understand the question of saving time, because basically stating that the expectation of epsilon t and variance et is basically my first and the second bullet point, and you need to add the third bullet point, which is the covariance, and then you have restated the uh, exact same definition that I have on the slide. So I don't quite understand what you mean by saving time. What I would advise you to do is not to just write epsilon. I would not just write this and this. I think it looks a bit sloppy, quick. Also, you're more likely to make mistakes. Be precise in your answers. Um, okay. Then we have to provide some intuitive discussions why this is important. What I would do is I would try to contrast this with the IID assumption in cross-sectional settings, right? In cross-sectional settings, everything we do relies on this assumption that the errors are independent and identically distributed. But that doesn't make sense at all in a time series setting, right? Um, if you look at a time series, and you've all looked, for example, at GDP, right? GDP of the US or of the UK or whatever you want, usually these are trending and they go upwards, right? That does not look like it's a it's a stable IID process. Yeah. And so basically these assumptions of covariance stationarity, they do replace these assumptions in order for us to kind of be able to still use our methods. Yeah. Okay. Um, Recognizing that the errors exhibit autocorrelation. So here the question is kind of phrased very nicely in that it's hinting to you again that, there is this autocorrelation present. Discuss how we can conduct statistical inference on beta using the OLS estimator. Specifically discuss how you can test a hypothesis that the null hypothesis that beta is 0.7 against the alternative that beta is less than 0.7 using the OLS estimator. So the first thing to notice is that this is a one-sided hypothesis test, which is already where often people who go quick tend to make mistakes. And the other thing to notice, which is sort of hinted at in the question or kind of re-highlighted in the question very nicely, is that you're going to have to use hack standard errors, right? Because you have this autocorrelation in your error structure. Yeah, so you cannot use your usual or normal standard errors. Okay. And then the way you should go is what I call the usual steps of testing. I can tell you if you don't do this, you lose points. So, do this. We will see it a few times today. Sorry, to say that covariance stationary replaces. No, it's not correct. I mean, covariance to patient. No, no, no. Those are, don't think of it this way. Don't try to map one into the other. The point is more that in time series settings, you have these trends and you have these dependencies over time, and we need to make the process stable. So oftentimes first we kind of detrend or we difference the process to kind of make sure that it is stationary or covariant stationary. And then we can apply the methods that we used before. And the stationarity, because it kind of restricts these moments, so the mean, for example, to be not changing over time or the variance, it makes sure that the process is stable, right? And it gets rid of this dependence of this spuriosity of that regressions might have otherwise. But don't think of it, I wouldn't kind of one-to-one link it to identical or independence. So stationarity. So in theory, the definition. So just to be very precise, the definition of stationarity is different than there's stationarity and covariant stationarity. Yeah, those are different things. You're only dealing in theory with covariant stationarity, though I understand that sometimes you're using the same word. Stationarity is a stronger concept, which says that the whole distribution is equal under time shift, whereas covariant stationarity, we only say that the first and the second moment, so the expectation and the variance and the covariance are equal under time shift. Yeah. So first of all, those are the same. They're both very important for you to be able to apply uh, or for kind of weak law of large numbers and the central limit theorem to exist. So you need those. Weak dependence goes into that direction, yes. So you need covariant stationarity for these things. Do we have to add the full statement here? Let wait, the last thing on the T statistic I'll answer once I've gone through it. Um, okay, we do okay, so we have to test these hypotheses. We have the null hypotheses. So the first thing you have to do is you have to state the hypotheses again. Yeah, I know they were stated in the question, but trust me, you don't state them, you lose points again. So don't be quick. Also, hopefully this helps you because it makes you see that it's a one-sided test. The next thing you do, you have to tell us what is the statistics you're using, right? Is it an F test, a T test, a likelihood ratio test, a WALP test, whatever it is. So in this case, you use a test T test. Okay. So then you tell us, okay, the T statistic looks beta hat minus beta. Okay, what is this? This is the estimator. This is minus the value under the null divided by, in here, it's a very big advantage that you write hack standard errors and not just standard errors, just to again highlight that you're using and that you're aware of this autocorrelation structure in the error. Yeah. Then if you know the values of beta hat and the standard error, you plug them in and you calculate the number. We will see this later. Of course, here we don't, so we just plug in 0.7 for the value under the null. Then what you need to do, right, is sort of tell us here what you would do with a tilde, what is the distribution of this? And here comes to the question. Yes, you can just do that this is distributed, follows a standard normal distribution. I have added this explanation here just for you, which you don't have to go through, but the point is that we are in a time series setting with autocorrelation. And so we have to use the asymptotic normal distribution, yeah, standard normal distribution. In a cross-sectional setting with the t-test, right, in finite samples, you also have the exact t-distribution. We'll see this later, but here we must use the standard normal. But yes, you can just write tilde standard normal to answer the question, and that's of course fine. But this was meant to explain this to you. The next thing you do is you say the significance level. Again, unless otherwise indicated, I would use 5%. I think that's sort of the standard, but feel free to do what you want. And then you go look up the critical value in the table that's going to be given to you. Yeah. And so the critical value is minus 1.6. It's a one-sided test, so make sure you know how to read these tables. And then you have to say what the rejection rule is, right? So we reject the null hypothesis if this test statistic, right, the t-value here is less than minus 1.6. Yeah. And if you, of course, had numbers, you could also conclude I reject or I don't reject or something like this. Yeah. Okay. So these are always the same steps. You have to state them all. Consider the following time series model. Now we're regressing y. Hold on. So for question 1A, if 1B, it would not be fine to show heteroscedastic robust standard errors. Because the question asks how you can obtain the best linear unbiased estimator, which heteroscedastic robust standard errors don't get you, right? Only you need homoscedasticity to get a blue standard error, which means you have to transform the model. So you cannot just do robust standard errors. Okay, so we have this time series model where we regress y on a constant, a time trend, so just beta t plus ut. And ut follows this AR1 process, which means we are regressing ut, where an AR1 process is ut is equal to rho ut minus 1 plus epsilon t. And the absolute value of rho we are given is less than or equal to 1. And epsilon t is a white noise process, meaning it's IID with mean 0 and variance sigma squared. Yeah. And that's covariance stationary. Yeah. Okay. You also call it stationary simultaneously, but that's covariance stationary theory. Show that yt is trend-stationary when the absolute value of rho is less than 1. Yt is trend-stationary if by detrending we can make yt stationary, right? So that's sort of the definition of trend-stationary. So what does it mean to detrend? Well, we just subtract the trend. Well, the trend is beta t. So this is sort of lucky that we're regressing this on a trend. So we have yt minus beta t. We're left with alpha plus ut. And so now what we need to know is whether the RHS stands for right-hand side is stationary, right? If that's stationary, then we have basically yt being trend stationary. Well, alpha is just a constant, so it's not really influenced this. I'm not really going to influence this. And so what we need to figure out is whether ut is stationary or not. But ut is an AR1 process. And what we know from the lecture is that an AR1 process is indeed stationary if rho is less than 1, which is the condition that we have here. Yeah, so hence this yt is indeed trend stationary. Yt is different stationary, or show that yt is different stationary when rho is equal to 1. So what does it mean to be different stationary? It means that if by differencing, if when I difference the series, I can make yt stationary. Yeah. So let's first figure out what it means to difference a series. Well, you have the model given. Let's just look at what happens if I look at it yesterday or at the period before. So that's just yt minus 1 equals to alpha plus beta t minus 1, ut minus 1. Now we need to subtract one from the other, and that's the difference, right? So we're going to call it delta yt, which is just equal to yt minus 1. Alpha minus alpha cancel. Beta t minus beta t cancel. Minus beta becomes beta. ut minus 1. So this is the difference series. Okay. Now let's look again at the AR1 process. But notice that the question says that rho is equal to 1. And so if rho is equal to 1, this AR1 process becomes this. Right? Because rho is just equal to 1. So now you can just do ut minus 1 is equal to epsilon t, which is this, right? We just put this to the other side. But why do I do this? Well, here I have ut minus 1, which is exactly what I have here. So I can replace this with epsilon. And so I have that the difference process is equal to beta plus epsilon. And so now again, we need to figure out whether the right-hand side here is stationary. Well, beta is a constant, so we don't care about this term. And epsilon t is white noise, which we know is stationary or covariant stationary, if you want to be very precise. Yeah? And so yt is different stationary. The third or last question here is about distinguishing or discussing what the difference is between trend and difference stationarity. What I would discuss here is the implication for the long run, right? Or just what these series do. So a time series that are trend stationary is always going to revert to a trend. Yeah, so there might be a shock, there might be a recession, but then we're coming back to the trend that we're on. So if we're on some sort of trend here, we're going, there might be a shock, but I'm coming back to my trend. Yeah, so I might go up and down, but I come back. So there's weak dependence. The time series, which are different stationary, never recover from shocks to the system. Yeah, so those, I don't know, there's a trend and then the trend changes, right? So there's really a change in the trend. And those are permanent, those are kind of more structural changes, and those will not be temporary. Yeah, and so there is strong dependence or persistence of the effect. Yeah. Okay, that's what I would discuss in that question. Okay, question 5, let's define the term multicollinearity and provide a real life example where this problem is likely to occur. Multicollinearity means that some of the regressors on the right-hand side can be written as a linear combination of the regressors. Yeah, so for example, you could have that one of the regressors is almost equal to here, because we're not asked about perfect collinearity, right? It's just like some high collinearity is almost equal to some linear combination of some xj, which are other regressors. Yeah, and you might weigh them by lambda. Yeah. In words, multicollinearity indicates that there is a close linear relation between the regressors. In kind of simpler words, any of these regressors might be just highly correlated to each other. Yeah. Again, they're not perfectly correlated with each other because that would be perfect multicollinearity. Yeah. For an example, there are thousands or hundreds of thousands that you can choose from. An example is, let's say we want to explain educational attainment, so like test scores, for example. So the outcome is test scores, and on the right-hand side, we have a bunch of cognitive ability or cognitive skills measurements. All of those different measurements might be very highly correlated. Yeah. Notice one thing, just I would not in a question like this talk about the dummy variable trap, right? So for example, dummy variable trap is like, that you cannot, if you have a variable that's urban and rural, one for urban and one for rural, just two dummies, right? One perfectly explains the other. So you cannot include both in the regression because they're perfectly collinear, they're perfectly correlated. But that's an example or a special case of perfect multicollinearity, but not near or very high collinearity. Yeah, so I would not use the dummy variable trap here as an example. The second part of question 5 is asking you to read two statements and to say whether or not they're true or false. So the first statement is basically saying in multiple regression, multicollinearity implies that the least squares estimators of the coefficients are biased and standard errors are invalid. So then you need to think about the Gauss-Markov assumptions. And you see that, okay, yes, perfect collinearity is an issue, but near multicollinearity is not a violation of those assumptions. So all else estimators are unbiased and their standard errors are going to be valid, right? So again, it's just about not thinking that multicollinearity implies perfect multiple collinearity. Yeah, so the statement is false. If the coefficient estimates in an equation have high standard errors, this is evidence of high multicollinearity. Here I would pay attention. So again, right, it is true that if there are larger standard errors, that this might be evidence of kind of high correlation between the errors, between the regressors, but it doesn't have to be, right? We can also get high standard errors because we have a very small sample size or because we have a very large variance of the disturbance term. So there's a lot of other things that could also be at play. So the point is just to be very precise in how you read the statement, right? It's not absolute evidence that, we have multicollinearity or high multicollinearity. It could be, but it doesn't have to be. And therefore, the statement is false. Yeah. So I'm not the one who writes these exams, but these statements tend to be sort of made a little bit to trick you. So my advice would be to be, kind of slow down and go as precise as possible. All right. So this up to now basically were the short questions. So we took about an hour to do them and to go through all of them. So you see a little bit, right? You don't have to write like a monologue for these answers. Of course, I'm trying to explain things to you, so I speak a bit more around it. But you sort of get the idea of how these short questions go. The long questions are, of course, much longer, as you will now see. Um, yeah. All right. So we're just going to go into question 6. This is the first long question. What it says is that we are interested in explaining the willingness of households to buy ecologically produced apples. We're using data where each family was presented with a description of ecologically friendly apples along with prices of regular apples and prices of hypothetical eco-labeled apples. So you have reg price and eco price as these two price variables. The outcome we care about, or the variable we want to explain, is a dummy variable, which is called eco-buy, which is equal to 1 if the household wants to buy ecologically friendly apples, and it's 0 otherwise. Yeah, so it's a dummy. Additionally, we have some control variables, which are the family income in thousands, household size, the year of schooling, and the age. We have a sample of 660 households, and we obtained the following results, which are, in my case, on the next slide. Also, we are told that heteroscedasticity robust errors are reported in square brackets and standard errors, asymptotic standard errors are reported in parentheses. So these are the results, right? So the outcome would be kind of here. Maybe it would be nice if they had written this. It would be this variable eco-buy, right? Which is this dummy variable that is equal to 1 if you would be willing to buy the eco apple, 0 if you're not willing to buy the ecologically labeled apple. Yeah. In the first column, this is an OLS regression. So you're just regressing the outcome on a constant on the price of regular apple and on the price of eco apples. In the second and the third column, they're running probit models instead of an OLS, right? An OLS, by the way, is equal to what? Is equal to the linear probability model because we have binary outcomes. We'll see this in a bit. Probit A is just, again, regressing the outcome on a constant reg price and eco price. Probit B is doing the same, but is adding all these control variables, these 4 that we have. Yeah. And finally, for OLS, because we're using the linear probability model, right? The linear probability model, because it's a binary outcome, if you look at the variance of a Bernoulli variable, right? The variance of a binary variable, of a binary random variable, is the probability that y is equal to 1 times 1 minus the probability that y is equal to 1. And so the point is it depends on x. And so you need to have, in the linear probability model, you have heteroscedasticity inherently in there. And so when they run OLS, they need to use robust standard errors, right? And so these are here in square brackets, which is what's written here. whereas the probit model or MLE is implicitly taking care of this. And so these are different standard errors, which is why they're kind of denoted differently. Okay? Okay. Carefully interpret the estimated coefficient of the price of ecologically friendly apples reported in column OLSA and discuss whether the effect is statistically significant. In your answer, explain why it is important to use robust standard errors. Okay, so the first thing I would do is I would try to figure out which coefficient are they interested in. So it's column OLSA, so it's one of three. So if you're just guessing, 33% chance. And then it's the impact of eco price. So this is the coefficient, minus 0.8, right? So the first thing I would do is I would just write down the coefficient, because if you get the interpretation wrong, at least you're going to get some points for getting the right coefficient. Then for the interpretation, right, what's the interpretation? Well, if the price of ecologically produced apples increases by $1, the probability that households buy ecologically produced apples, it decreases by 0.84. Yeah? Ceteris paribus. So what I'm trying to say here is this is kind of the standard sentence that you know. You should add ceteris paribus because you want to highlight that it's all else equal. You should, second of all, I would write no more than one sentence. Usually people who write multiple paragraphs or 2 or 3 sentences start off with the perfect sentence and then in the next and following sentences add mistakes, which is just like, don't do it. Just have like one sentence always the same. And the third thing to highlight is don't use words like causes, right? You don't want to use causal language. So just say, if one thing increases by one thing, you 1 unit, this is the impact that we see. That's it. Or is associated with is a great thing to use, right? Okay. Why is it important to use robust standard errors? This we already said when we looked at the table, right? In the linear probability model, there is this inherent heteroscedasticity in the error term because it's the error term of a binary outcome. Yeah. And I just said before, the variance of, if you look, for example, at the variance of a binary variable, it's equal to the probability that y is equal to 1 times 1 minus that probability. And so that depends on x, that probability. Yeah. Okay. To test for the significance, here again, you're going to see it. This is going to be a bit quicker, but again, you need to go through all the same steps. Yeah. So first, you state a null and an alternative hypothesis. So the null hypothesis is pretty clear. It's that the beta on eco price is equal to 0, right? That there's no significant impact. The alternative, it's not really said, so you can choose what you do. You just have to clearly label it. It could be a 2-sided test, it could be a 1-sided test. I always find the 2-sided test the simplest, so I do that. Then, again, you tell us what you're doing. I'm doing a t-test, so the t-statistic is beta hat minus beta, under the null is null, divided by the standard error. Well, now I can actually calculate this, right? Because this is minus 0.8 and the standard error is 0.1. Minus 0.8, 0.1 is minus 8. Okay, so this is the test, the t-value. Now, we are in a cross-sectional case. If you think we are in finite samples, this test statistic follows a t-distribution. If you think we are in large sample theory, then you think that this follows a standard normal distribution. In this case, we're given 660, a sample of 660 people. So to me, it's always easier to work with large samples. So I use the standard normal distribution, but if you wanted to highlight the other one, that's also fine. Okay. So here I say what the distribution is of this test. Then 5% significance, what's the critical value? 1.96. Okay, this one we probably know by heart, but if not, again, you have the table in the exam. What's the rejection rule? Well, is the absolute value of the t-value greater than 1.9? In our case, yes. So therefore, we reject the null hypothesis. And then you do some final statement, which is saying that, okay, I conclude that this impact or this effect is statistically significantly different from 0. Yeah. So as you see, again, each step is there. And if you forget one of those steps, if you just immediately jump to a conclusion, you're going to get very few points. I'm not the one making these rules. Okay, it is argued that using the probit model is better than using the LPM when explaining the binary variable ecobi. Discuss the benefits and the drawbacks of using probit when trying to explain a binary variable. In your answer, explain what the LPM refers to. So let's start with the end. What is LPM? Well, linear probability model is just a special case of a binary model, right? So the point is to realize that when the outcome is binary, I mean, it doesn't really have to be when the outcome, for any binary variable, right? The expectation of that variable is equal to the probability that that variable is equal to 1, yeah? Which is basically what this is saying. So if y is binary, then the expectation of y is equal to the probability of y, equal to y being equal to 1, yeah? And in a case where we have a binary outcome in a regression, what we care about is that we want to look at this, right? We are interested in this object. What's the probability that y is equal to 1? But because this is equal to this expectation, we can also just use OLS. And that's called linear probability model, because here we are assuming that that probability is linear in its parameters. Okay. Okay. What are the advantages of probit? Well, an advantage is that the predicted probabilities lie within 0 and 1, right? So probability is always between 0 and 1, whereas with LPM, they can sort of go below and above that bound, those bounds. We know that OLS and LPM has inherent is inefficient because of this heteroscedasticity. MLE is attaining something called the Kramer-Rao lower bound, which is nothing other than saying basically that there's a theorem that proves that it attains the lowest possible bound that it can attain in terms of its variance, which means it has the smallest possible variance, yeah, of all estimators. So it's more efficient than OLS, yeah. MLE automatically deals with this heteroscedasticity, whereas in LPM, we would have to adjust the standard errors. Yes, sorry, we have to use robust standard errors. And an advantage is that the marginal effects, as we will see in a little bit, are allowed to depend on the right-hand side variables, right? In LPM, the marginal effect is just constant, right? It's just the coefficients that you're estimating. And that's quite a difference. This, however, is also a drawback because it means that in probit, those coefficients that you're getting, that we're seeing in the table, we cannot give them any interpretation, right? For the OLS, we can give them interpretation because the coefficient is equal to the marginal effect. In the probit model, as we will see in a bit, that's not the case. Yeah, so we need to first compute those predicted probabilities. There's another drawback, which is, however, a bit less relevant, I would say, in a lot of applied work, which is that it's computationally more complicated. In many things, like, for example, this application, probit and LPM a computer needs the same time. It has to be very, very complicated for MLE and to start working so much that it's an issue. And so it is computationally more complicated, that is true, but oftentimes in reality, especially in applied work, this is not that much of a difference or not that much of a drawback. Okay. Probit model B postulates that the probability that ecobi is equal to 1, conditioning on x, is equal to the standard normal CDF evaluated at all of this, right? This should make sense. That's just this. Probit model B is equal to the constant times the two price variables and the four controls. Sorry, I see there is a question. Sorry to bring this up again. Sorry to bring this up. This is from the commentary. Which commentary? Assumption. Ah, okay, commentary for an exam. Okay, then sure. Sure. Then let's say, I mean, if that's what's written in the commentary, that I'm not saying, by the way, that weak dependence is not an important concept. Huh? That's never what I hinted at. And I am saying that they are very important because thanks to them, thanks to these assumptions, you do have these weak law of large numbers. The crux is a little bit that the weak law of large number that you hold, that you learn, right? So, okay, let's put it differently. The weak law of large number, so the same will hold for central limit theorem. The weak law of large number that you learned in IID setting or in cross-sectional data assumes that the data is IID, right? So then that's a theorem, that's a weak law of large number that holds under that thing. In time series data, that theorem will not hold. So now you need a new weak law of large number, which will have new conditions, and that will be the time series weak law of large number. And those time series weak law of large number, they need weak dependence, and yes. So I agree with that. Um, that it's a one-to-one mapping between weak dependence and independence. Okay, fair enough. If that's what they say, then fair enough. I don't necessarily think of it this way. I think of it more as two different theorems that ultimately are both being applied as weak law of large numbers, but they need different things. But yes, it's fair to think that maybe it replaces this idea of independence before. Does that help? Great. And someone raised their hand. Can you unmute yourself and speak? Is that possible? I think now you can speak. Darani? Darani, do you have a question? Okay. Okay. I'm going to continue because I don't hear you. If you are asking a question, I don't hear you. Maybe I'm the only one. Maybe try to uh, type your question like the others have. Okay. So here we are. Uh, okay. So model B, the probit model B is going to postulate that we have this model, right? This is what we just looked at before. And the question is telling us use the likelihood ratio test to test the joint significance of the non-price variables. Clearly indicate the null and alternative hypotheses, the test statistic, and the rejection rule. Okay. So what's the null hypothesis? Basically, we are testing whether these controls matter. Yeah, so there's four of those, and we're testing whether or not they're equal to zero or not. So the null hypothesis is that beta 3 is equal to 0, beta 4, beta 5, and beta 6 is equal to 0. Yeah. The alternative is that at least one of them is not equal to 0. Okay. So we are already told which test statistic we have to use, which is the likelihood ratio test. Now, the thing about the likelihood ratio test is that the way it works is that you will have probit model B is essentially the model where you allow the controls to be in there. But if you impose the null hypothesis, then you set the beta in front of all of these four variables equal to 0. So then you get the restricted model. And that turns out to be probit A, right? And so what you see is that if you look at the formula for the likelihood ratio test, is you need something from those two models, namely the log likelihood. And so that's given down here. Yeah. And so the test statistics of the likelihood ratio test is given by this, which is 2 times the log likelihood of the unrestricted model, that's model B, minus the log likelihood of the restricted model, which is model A. Yeah. So if you plug in those two numbers from the bottom of the table, what you should get for the likelihood ratio test statistic is 17. Yeah. Then you need to write down what the distribution is here. That's a chi-square distribution, right? With 4 degrees of freedom. Why are there 4 degrees of freedom? Well, that's because we're testing 4 restrictions, right? Where the family income, household size, education, and age are equal to 0. So there's 4 things. Another way of thinking of this is there's 4 equal signs here. Yeah? Okay. Then again, what's the significant level? 5%. What's the critical value? You go look at a table. It's 9. 17 is larger than 9. Therefore, we reject the null hypothesis, right? So therefore, at least one of those variables seems to matter, or seems to be statistically significantly different from 0. Yeah? Okay. So hopefully it's clear that this is, again, kind of the same steps of the procedure. Okay, the last question here is that here we're interested in the marginal effect of the price of ecologically friendly apples using probit model A holding constant the price of regular apples. Indicate how you can obtain the marginal effect of eco price using the probit model. And then the second part is, unlike in the LPM, this marginal effect will not be constant. Discuss what computations you would carry out to obtain the marginal effect of a 10-cent reduction in eco price when evaluated at the mean of explanatory variables. And we're given the mean price of these 2 price variables here. The crux is that you're not expected to use any calculator. You're just expected to sort of show how you would calculate this. Yeah. Okay. So let's first think about what the marginal effect is. So the first thing to notice is that model A is just the outcome. So the probability that people buy this apple is equal to the CDF, the standard normal CDF on a constant, reg price, and eco price, right? That's model A. That's the probit model. So what's the marginal effect? Is you just take a derivative with respect to eco price. Well, how do you take a derivative of this with respect to eco price? Well, first you do the outer derivative. So you get a PDF evaluated at everything. And then you do the inner derivative where you just get beta 2, right? And so this is sort of where you see what we talked about, or what I said when I said about the advantages and maybe also disadvantages of the probit model and the marginal effect. The advantage is that the marginal effect here is not just the coefficient beta 2, right? In an OLS model, it's just beta 2, it's just constant. But in the probit model, it's beta 2 times this. And so it depends on the price that you plug in. And so you can get marginal values for different values of prices. Yeah. But simultaneously, it also means, of course, that the beta 0, beta 1, and beta 2 have absolutely no meaning, right? Because the marginal effect is this whole thing and not just this. So in OLS, at least, you see beta 2, you can immediately interpret it. In probit and in logit as well, you need to first calculate this whole object in order to be able to find it meaning or to give it meaning. Yeah. Okay, now the whole thing, there's a question. Yes, you need to write the assumptions. That's a good point. So in testing, you should also write down that you're relying on the assumptions, MLR, whatever they are. So, I mean, for standard normal, those are the exams. Those are the symbols, right? So if it's a probit and you're using a standard normal CDF, it's this one up here. If it's a standard normal PDF, it's this one down here. If you're doing a logit or a different distribution, then you can use G and G or whatever you want, and you just kind of write G of Z, where G is equal to the standard normal, the logistic distribution or whatever you want to call it. And another question. I mean, I'm not the one grading your exams, so I don't know about whether or not I would write them with the math, would be my hunch. And you don't necessarily have to mention them at the beginning of the exam, right? You can just mention them throughout when they come up. That's up to you. I'm saying it's up to you how you do this, but you have to mention them at some point in the exam. Okay, so the point is, let's finish this question. I mean, I can stay a bit longer. I'm not trying to rush, but just in case you guys have to go. The point is, this is the population marginal effect, which of course we never observe. So what we have to do is put hats on everything, right? Because we're estimating things. And then we can just plug in these values, right? Because now we know actually what this looks like, right? Beta 1 hat is 1, beta 2 hat is 2, beta 3 hat is minus 2.3. So you can plug in 1, 2, minus 2.3, and here also minus 2.3, right? And so now if we plug in some values for prices, we actually can estimate this value. Yeah. And indeed, what the question is telling us, part two, is that we are going to evaluate this at the mean. So at the mean means you plug in 0.80 cents for reg price and $1 for eco price. So you're going to plug in 80 cents here and $1 here. Yeah. And then what you have for part two, the marginal effect, is given by this expression here. Yeah. And this you can calculate. Now, you don't have to calculate this in an exam, let me be clear, because this is a standard normal and it has, pi in there and square roots and I don't know what. But you need to, one could put this in a computer and it gives you a number, right? The point is this is a number that one could easily calculate or a computer can easily calculate. Yeah. Now, what the question is asking us, sorry, is discuss what computations you would carry out to obtain the marginal effect of a 10-cent reduction in eco price, right? So is this the marginal effect of a 10-cent reduction? The answer to this is no. This is the marginal effect of a $1 increase in eco price, right? And so what we need to do basically, or one option in which we can get the marginal effect of a 10-cent reduction, is to just calculate this number and then multiply it by minus 0.1. And then you're done. That could be the answer to your exam. A secondary way which you could do it is to just kind of go back to the CDF and plug in the estimates here, right? So if you plug in beta hat 0, beta hat 1, and the average price, and beta hat 2 and the average price, you get the probability that people buy the ecologically produced value, the ecologically produced apples under average prices, which is exactly this. This is the probability that people buy these apples under average prices. But then you can calculate the same probability, where again you have the constant, the coefficient of regular prices, and the average 80-cent price for regular apples. And then you do the coefficient on eco apples, but for the price, you do a 10-cent difference, right? You do minus 10 cents. And you calculate this value. And the difference between those two probabilities will be the same as the impact you would get up here. Okay? So you don't have to do both, but you could write one or the other. Okay. So we are sort of nearing the end of time, not the end of our time. So I'm going to stop here. Again, the rest of the slides go through all the questions. So I will send this, or I will have, because I don't know any of your emails, I will have someone send this to you, so that you have access to all of this. Um, do you have any questions? Okay, I take the silence and nothing in the chat as meaning no questions. Maybe there is a question. So when you should be getting the slides, I mean I so it sort of doesn't expect depend on me. I will send them right now to someone. Then from what I know, that person is out of office today because she told me. But hopefully within tomorrow you should get them. But I will email them in the next 5 minutes. So from my side, this is going to be done right away. Um, but if you saw my email, if you don't get the slides in like a week, maybe email someone and try to ask about it. But I think it should happen right away. In the past, this has happened very quickly. One person wrote down, here's the second part. Do we have any any table or anything you would need would be, I mean, I'm not responsible for writing your exams, right? Uh, so I don't know the details of this, but in general, if you need to know a critical value for any test or any distribution, uh, then you will get the table for that distribution. So I hope this answers the question, Liang Yu. If not, please write another question or a follow-up. Uh, can we screenshot the rest of the questions? You mean of my slides, but you will get those slides, no? Or what do you mean by screenshotting? I'll send you the whole slide deck. I'm not just going to send what I've done today. So you should, I am guessing by tomorrow you have the whole slide deck. I mean, my advice, and yes, so Kaiwei for the T and Fs, I would always use 5% significance for any test unless otherwise indicated. I think it's the standard that people use, and so this is the best way to go. I think you're sort of digging yourself a grave if you start using 7% or something like this. Do you have any other questions? Okay. I'll take the silence as that there are no more questions. So thanks very much for listening. I hope this was a little bit useful. Um, I'll send those slides over, so you should have them right away tomorrow probably. Um, and yeah, good luck in your exams. That's the most important thing. I hope you all do well. Have a good day and goodbye.